And yeah, so this talk will be actually mostly based on what I'm doing as a mentor for this. So yeah, thanks.
Give it up for Camille.
Thanks for being here. Okay, I'm asked to put this tracking watch. So just before we start, I just want to make sure your expectations are, that we match expectations. So it's really a beginner introductory talk on recommender system. It will be mostly focused on collaborative filtering and matrix factorization. So who have ever heard of the term matrix factorization? Okay. Among those people who have ever worked on a recommender system? 1, 2, 3, 4, 5, 6, 7. Okay, so actually this tutorial, thanks. So this tutorial is not aimed at you. So either you want to, make best use of your time, or you want to stay here and help me if there is any question, or during the hands-on, make sure that you help your neighbors around. All right. So who has never heard about matrix factorization? Okay, so there are a few, or who have never really touched recommender system. So yeah, so that tutorial is aimed at you mostly. Oops. All right, so as we mentioned before, I am the data scientist at Booking.com, so that's why I still put the slide of Booking.com. However, this hands-on is inspired by one of the projects of the program I was mentioning, and at Booking, I'm not working on recommender systems. I work on experimentation, helping teams to assess the impact of their changes through mostly A/B testing and methodologies. So yeah, none of this reflect the work we do at Booking on recommender system. This being said, I'd like you to actively participate. Please ask questions when you have them. Let me know if you don't follow or if you don't understand something. Chances are, if you don't understand, probably your neighbor doesn't understand either. So do raise your hand and ask. Yeah, let me know when you don't follow and help each other during the hands-on. So what is a recommender system? I'll just define it as a type of information filter which aims at proposing relevant pieces of information. So for instance, when you go on Netflix, you'll be proposed a few more movies to watch. When you go on Amazon.com, you'll see a product that you might be interested in. If you go on a travel, on an online travel agent, then you'll be proposed recommended properties to go or even destinations. During this talk, I'll be mentioning ratings. So ratings could have many forms, and I just have a distinction between two. So it's an expression of users' interest. You can have explicit feedback, like you ask someone to rate a movie and put stars. You ask someone to rate an app on the App Store. Yeah, so it requires some kind of active action from the user. But we also have available something like implicit feedback. So linked to passive actions to the behavior. So if someone browse the website and see one page rather than another, click on some button, look at products, the frequency they come back. So all of this can give us also kind of an implicit rating, implicit feedback. Also, okay, there are many different kinds of recommender systems. We also talk sometime about ranking method or ranking algorithms. So here I'm just focusing on two big kind of recommender system. One kind which is called content-based. So we don't really care about user interaction with your website or your product. We only look at what products you have. So you might have movies, you might have product like on an e-commerce, you might have, I don't know, a news website with articles. These are also kind of products. And so the content-based methods to recommend systems, they just try to find similarities between the products you have. So you could look at you could look, I don't know, for a movie, you could look at the budget, you could look at the actors, you could look at the genres, etc., etc. And to find similarities, you can use neighborhood methods, so really looking for similarity between products, or clustering methods. Another big kind of recommender systems is called collaborative filtering, and it is based on really the social interaction of the users. So it's really how users interact with your website, how they browse your products, and so on. And among this big like group, there are like 3 that were kind of popularized. User-based, so you look for similar users from this user-item interaction. Item-based, you look for similar items together. And matrix factorization is you look at, well, you try to kill two birds at one stone. So you really try to recommend the best product to the user given the past interaction of all users with all the products. So just if I take those 3 examples, I'd like you maybe to tell me whether it's implicit or explicit feedback, and whether it's content-based or collaborative filtering, and if you can maybe tell me which kind of collaborative filtering it is. So Netflix, here, because you watched Stranger Things, then we're proposing you those films. What would it be? Would it be implicit or explicit? Implicit feedback. Yeah, someone who would fall for explicit? No. Yeah, this is really, we didn't ask the user here to rate something, but we just observed the behavior of the user. You watch this movie, and probably using an item collaborative filtering method, then we come up with recommendations. Amazon, customers who viewed this item also viewed those items. Again, it is implicit feedback, and what kind of system would it be? Sorry? I don't hear. Sorry? Content-based? Yeah, well, actually, here you still have the customers. So, so you probably have used some kind of user item metrics or user item list. So it's still collaborative filtering, and also actually probably item-based. And the last one, so online travel agent. Our topic, so here, I don't know, I see, oh, Camille is still interested in Fairmont Austin. So what would this one be? Yeah, it's not maybe obvious. It is still implicit feedback. So actually, most of the cases here I gave you are implicit feedback. It means like we got a huge quantity of data from that. And this one seems like very personalized, like it's me. It's not like anyone else. It's not like those customers who viewed, like it's me, it's targeted at me. And it's probably something that use either matrix factorization, I don't know exactly, but it's really trying to make the most use of the information, user item information. So now we'll dive in right into collaborative filtering. Most of it will be about matrix factorization, but first, so what do we say, why do we say collaborative filtering? So actually, the start of this kind of methods is having a list of ratings. So you have a list of pairs user item to which you have an associated rating. So here, again, this rating could be got explicitly. So here, I think I just got a rating from, for instance, a movie databases where people actually clicked on it. But you could come with some kind of rating with maybe the frequency of viewing such a page or something like that. So it doesn't have to be explicit, but well. And so yeah, you see that. So let's say it is sorted by user ID. So okay, user 1 has rated 2 items. User 2 has rated 1 item, and well, none of it is common with user 1. User 57 has rated 3 items, and one of them, actually 2 of them, are common with user 1. And from this, what you want to get, or maybe it's easier to represent it, you just pivot. I don't know. Is anyone not familiar with NumPivot? It's okay, please raise your hand. No one's raising their hand, wow. Pivoting a table. So, so you're not beginners, you cheated, right? Yeah, okay. All right, so you get, so by pivoting this on user items and then filling it with the ratings, yeah, so you get what we call a sparse metric, meaning that most of it is actually non-filled. Most of it is missing values, but you have a few values that are non-missing, and that's the information you get. And so you got this, and this is the base of many collaborative filtering methods. So one of them that I was mentioning, I will be very quickly on it, is the user-based methods. So here you would consider that, so you focus really on the users, and you will consider all the items. So it could be the movies that they rated, and so you see that you have a few ratings, a few missing ones. I mean, actually a lot of missing ones. But here you will consider that the items are kind of features, and you will use these features to find the similarity between users. So you will take, for instance, user 1 and user 57. You will compute some kind of distance between the two. Usually we use cosine distance. And you will come up with, like, user 1, user 57, path with this value here. And you do the same for all pairs of users, and you end up with a symmetric matrix, which give you kind of the correlation between users. And from that, then you can work on building a recommendation. You know user, you see how similar it is to another user. This other user has like these other products, and then you can recommend those other products to the first one. So yeah, you start from a n user by n items metric, and you end up with a symmetric matrix, n user dot n user. Item base is actually the opposite. This time, these are you focus on the items, and all the users are actually kind of features. You do the same. You take two items, for instance, item 1 and item 2. You try to find a similarity between these two vectors, and you find a value here. And you end up with a symmetric matrix of n items. And from that, you can find, you can recommend products that are similar to some product that you've browsed. But the last method, okay, that I'm going to present today, and that's the one we'll spend most of our time today, is matrix decomposition. So you start from the same sparse matrix, user item, and again, it's a sparse metric. It's mostly filled with zeros. And eventually what we will want to do is to fill all these missing values. By doing so, I mean, or why do we say matrix decomposition? Because most of the methods try to focus on finding a matrix of users and a matrix of items that define the items, and trying to, like, the product should give you something close to the first matrix. So you start with n user by n item matrix. You try to decompose it in some kind of user matrix and item matrix. And the nice trick is, so it's a sparse matrix, so you should be able to find a lower rank matrix, meaning a matrix that contains, here you have like many dimensions for users, many dimensions for items, but actually the user or the items could maybe define by in a smaller dimensional base, like a space with smaller dimensions. So, okay, this is up to you to define or optimize this number of factors. We call them latent factors. They're kind of like hidden property of a product. So if you think of a movie, once you've, let's say, trained an algorithm to do this, maybe, so you get one factor, maybe this is around maybe okay, how much this movie contains like action, or how much this movie, I don't know, how old? Sorry. Yeah, maybe like so generous, but maybe it could be, okay, it's like a blockbuster or something around. I don't know. It has been directed by like a very famous like director, or yeah, but we don't know actually. Just the algorithm will try to find the most relevant hidden features, given this. Yes. Yes, you have to define it, but you can also try to optimize it. Yeah, that's something that you define somehow beforehand. But when you do so, this I didn't mention before. So you have the content-based methods that are mostly unsupervised. You try to find similarities between, between products, and this method is a supervised method. So you can really try to split between try and validation tests and try to optimize on the error to get a nice, an optimized number of factors. I don't know if it answers your question. Yeah. So I touched a bit. So how to interpret the user and item matrices. So here, all the columns would correspond to some hidden factors, and it's a characteristic an item can possess and a user can be susceptible to. If I take user u, so this value in the for the factor k is how much the user u is susceptible to this characteristic k, or how much it is important to them. Similarly, if I take for item I, this value here will represent how much this item possess, like how much of this characteristic the item I possesses. So like if you've done I don't know, some kind of scientific curriculum, at some point you've come up with one way to do matrix decomposition, and it is called SVD, for singular value decomposition. And it's exactly, on paper, it seems to be doing exactly what we want, which is come up with a lower rank approximation of the first matrix. So we're able to decompose the user item matrix into a user matrix and a vector matrix, and these are orthogonals, and we also find the eigenvalues of the original matrix. So that's, yeah, let's say we want to try this, like just to get some rating data, pivot, and get the user item matrix, and then apply SVD. Let's try that. So here is a short link. I can also copy paste it in the Slack channel. Oh yeah, just before. So who doesn't have access to Collaboratory? Okay, 1 or 2. Did you manage to download, to install the required packages? Damn it! I put like a long list to make sure people will go to Collaboratory, but okay, it's okay. Just go ahead. You have the 2 links. And also, while you connect, could you check that you have access to the Slack channel? So I created a tutorial 1 Rexes channel, so that maybe I can copy paste a few things there. It's this tutorial 1 Rexes. Up, 7 people, 16 people. I think we missed a few more in the channel. So I'll just put this stick. So I leave it on the screen. Who hasn't been able to open the notebook yet? Just to see how fast, a few more. So I leave this. Do you need the link still? Okay. Sorry? You got it, yeah. Nice. But okay. The people who didn't connect, are you able to connect now? Get it? If you didn't bring your laptop, I think actually most of you did, please make friends with your neighbor, ask if you can, have a look at what they're doing, and yeah. I see new friendship, starting here. Oh, so I remember there are a few people who might get bored because because they've already worked on recommender systems. So I've come up with a little game here. So there are a few flows in the notebook. It's not like I'm aware of some of them. Some I might not be aware of. My idea for this notebook was to get you, let's say, build from scratch, like only using NumPy mostly, a first, matrix factorization algorithm. So I did make a few shortcuts or stuff. So the game is, if you detect like some of the flows or like some bias that are there, you get 1 point. Sorry. Okay. All right. So yeah, if you get 1 point if you find a flow, if you think you find a flow but it's not, you lose 2 points. If you're able to actually find a solution or a fix, then you get a random number of points with an unknown probability distribution. Yeah, and if you reach -5, please, you're out of the game. And so the game, what you gain, I'll pay a drink to whoever who has the most points after this game. And also, yeah, I have the right to stop the game whenever I want. No, but we keep the scores, right? It's not, yeah, or like to postpone it to after the talk or something. All right. So I hope everyone has connected. Yes. Okay. No, someone. Okay. So let. It's accelerated. Yeah. So it's PyData, the network, and it's thank you. Accelerated. So you should have this notebook here. So, all right. So we'll just import a few libraries. You might not need Seaborn, but it's a nice visualization library. So let's try with this. It's a bit small. Yeah, okay, better. All right. Is there anyone not being able to connect or having an unfriendly neighbor that doesn't want to, to work together? No one. Perfect. So yeah, so we just import the libraries and we import the data. So you just have to click, and maybe you want to know what the data looks. So you have two matrices or two data frames in that case. One will give you some information about the movie. So it gives you the movie ID. I recall it item ID, the title and the genres. We won't mostly use this for the recommender system because this is about matrix factorization. So we'll mostly use the second one, which gives you so the user item interaction. So one row will give you the rating that the user gave to an item. You have a timestamp. You might not need it, but maybe it will be useful if you want to cut the data or to get the most recent data or something. I won't be using it. So now your work is, I give you 5 minutes, 5-10 minutes, I don't know, to do a quick exploration. So, go wild, do as you wish. Don't hesitate to use as many cells as you need. I give you a few hints here. If you've never used pandas or matplotlib or seaborn before, and don't hesitate to use the doc or use your neighbors. Yeah. So I don't know what you would like to be interested is, I don't know, what's the range of the rating, what's the range of the user ID and item ID. I would I would encourage you to focus mostly on the DF ratings data frame, because that's the one we'll be looking at mostly. So I don't know what would I do. There's a nice function called describe that gives you a few, like some stats on the data. Okay, it's too late, but I had a few USB keys for anyone who could not connect to Wi-Fi or GitHub or something. So I know if you crash, if the computer crash or something. Crashes. is someone like really stuck? Like, I have no idea what a data frame is. Please, speak. I can send you one of your, colleagues here. All right. Yes. Oh, sorry, I didn't say. So you please don't go go further. Like just do your explorations, and then that's all. This will do right after. So are you happy with your exploration? Who is like super proud of their exploration? Like you've done a scatter whatever pairwise scatter plot. You've done like really nice string graphs from Seaborn. You've done. Okay, someone mildly happy with the exploration. Ah, all right, not helping. All right, so I'll have to do some as well. Okay, I won't do anything like very fancy. I don't have much time either anyway. So I'll just get, for instance, the histogram of the ratings, just to know like how they are distributed. So a very quick way to do this in pandas is just to take the data frame, dot the column name, dot hist. Okay, so yeah. Only thing is, okay, it seems we have half integers values of rating, so maybe I should say which range I want. So a range. I think so. Like from the describe, I can see that the minimum rating is 0.5 and the maximum is 5. So I'll just get something around that. So 0, maybe 6, and then I want to go every 0.5. Okay, NumPy. Doesn't start well. Between what and what? Oh yeah, bins. I have to say what it is. Bins. I want those bins. Yeah. So yeah, just like distribution of rating, it seems we have a subset of users who are very nice and don't put very negative ratings of movies. I didn't mention this data set comes from the MovieLens database. So it's a website associated to a research group, and they develop like recommender system, and you can actually log into this website, create your account, rate movies, and get personalized recommendations. So it seems like those users on this website don't put low scores. They put mostly 4, and that's all. Yeah. Take another graph. Maybe you want to look at the timestamps. You could try to find some kind of very fancy, I'd say, like use, for instance, the datetime library to convert those timestamps into actual dates. I won't do that. I will just try to have an idea of the repartition of the timestamps. And then, okay. So it seems fairly uniform for this period of time. I don't know what happened there. Maybe they stopped the website for some time, and you see like more usage or more rating at least being given there. So for me, that's all. Let's say what I wanted to know is like the range of the rating, how how it's distributed, and what's the age, let's say, or what's the distribution in time of the ratings. Did someone come up with like an interesting thing to visualize or to explore? No. Okay. Yes?
I think there's an outlier in item ID.
Okay. Possibly, yes. In what sense? Which?
Some visualization, there is a very high occurrence of an ID of item like 0 or 1. Having that the ID like is very much more than all the other.
So in the frequency of the user. So you group. Nice. Wow. Are you using Collaboratory?
Using what? Sorry?
Are you using Collaboratory, or did you put it on your own laptop?
I'm using Cloud. Yeah.
Would you like to share the link in the Slack so that people can just see how nice plots you got? Yeah, thanks. So you just click on the share. It's like a Google Doc, right? So you click on share and maybe view or something, and then you give the link in the Slack channel. So then you'll be able to see the very nice pairwise. Thank you very much. You know, interactive. Yeah. So once so once we got that, actually, what we are interested in, if you remember here, I've told you that the first step for collaborating filtering methods is to get the user item matrix from the list of ratings. So that's what you do at the next line. So here, just try to find a way to get this user item matrix from the rating matrix. If you're bored, you can, share your awesome plots. You can check his awesome plots. You can play the little game I gave you. Yeah. We can have a coffee as well. So what we want is to get the DF ratings and pivot, and so I don't know exactly the format of it, but in the Jupyter notebook there is a very nice thing. When you open a bracket and you click tab, then you got the documentation in line. So okay, the index would be the rows. So I want the rows to be the user IDs. The column I want it to be the item IDs, and the value I'd like it to be the ratings. So I'll just write that down. So we said index user ID, column, I guess we have to put it in here. Column item ID. And values, rating. And this should work. Anyone would like me to copy paste it in the Slack, or yes? Okay, I'll do that. I'll do it from here. So if you look at it, I don't want to lose anyone. That's a beginner tutorial, right? So if you look at what it looks like, well, it does look like a sparse metric. A lot of missing values, written as none. You can look maybe at the describe. So again, what this matrix represents is just it's another way of writing the rating list. So we got for a given user, so user 1, for instance, we get all the ratings this user gave to all the films we got in the dataset. Something we didn't maybe check before. So you have about 10,000 columns. That means you got 10,000 films rated. If you checked a bit before, I think here it tells you that, no, it doesn't tell you here, but you have about 600 users. So yeah, eventually what we want to do is, I don't remember how many rows there was in the ratings. I think it's written maybe up there. If you do ratings shape. So yeah, 100,000 ratings. So they're on average like about 10 ratings per user. And we got, what did we say we got? We got 10,000, we get 10,000 ratings. Sorry, 10,000 movies, 600 users. So we get about, 6 million rows, 6 million values in this matrix, and we got only 100,000 of them. So it's really like not filled. It doesn't seem like it, like 100,000 ratings seems to be a lot. But eventually what we want to fill is like most of the values here in this matrix. So just to give you an idea of the complexity of the task. So anyway, let's go quick. So if I just take one user ID, then this row will tell me all the ratings that the user did and all the movie generated. So let's take the first 10 movies for user 1. So we see, okay, rated movie 1, 3, and 6. I won't do that. You can save that for later. Like you can save maybe the already rated IDs for later. And what we want to do, the purpose of this is to find a matrix of lower, rank. That means like rank is not a dimension, but that means that the information that this matrix gets could actually be shrinked to like some kind of object of dimension k, like a smaller dimension. So if we want to apply like basically just SVD, so singular value decomposition algorithm, we can't do it on a sparse metric. We need all the values to be filled. So what maybe happened like 10, 20 years ago, people would try to find a way to apply just brute force SVD to this kind of problem. And it would be like, what should I put in the missing values? And they come up with, okay, we'll put zeros, or we'll put the mean of all values. So that's what I'm, let's try something. So let's fill it with 0. So that's the function fill missing value fill NA with 0. And you got a matrix with a lot of zeros now. Here we'll just put it in an array. So it's the same thing, just it's not a data frame anymore. And this allows us to use SVD from SciPy or from NumPy. So that's this library. The nice thing about the SciPy's version is you can tell them, the function the number of hidden factors you want. So here I put 50. Voilà. It's quite quick, actually. It's quite efficient for this amount of data. And so we got the matrix U, sigma, and V. So these are, these matrices here. Who puts animation on the slides? Okay, so that's this matrix, and we get two orthogonal matrices U and V, and a list of eigenvalues. So you got this matrix, the user matrix, the list of eigenvalues, and this. And how would you get recommendations? Well, it's a bit tricky, right? I'm telling, oh, here is this matrix. Please factorize it. So get me two matrices U and V so that the product gives the original matrix. And here, what we want to get is the matrix back. So yeah, basically, we just want to do the dot product, or like the matrix multiplication of those two matrices. And this is done here. Oops, did something wrong? Oh yeah, thanks. Yeah. So yeah, sigma is here just a list of eigenvalues, but what we want is a diagonal matrix. field with a diagonal filled with these values. Okay, I might have to be a bit quicker. So, yeah, here you got it. Maybe you want to put it in some kind of a data frame format. So, pandas.data frame of that. Okay, it's just a bit nicer. So it is the same as before. If you look at, if you try to compare this matrix and the first one, it's actually a bit off. And why would it be? That doesn't count as a flow, right? I mean, I know it's flowed, so I told it first. Yes? Yeah, well, that would be the case for any matrix factorization. We really try to find a representation that, let's say, takes less space, takes less actual meaningful dimensions. So no, that's not it. Well, here, basically, we just said, here at this line, we filled all the unknown ratings with 0, meaning that we just assume that users would rate very badly all those movies they didn't see, which might seem off, right? And then we applied SVD to that to get, well, back something similar, so that the two matrices we got give if you get the product of it, give the ratings. So theoretically, this would read as user 0 rated movie 2 with, would rate the movie 2 with this rating. User 5 would rate film movie 4 with this rating, and so on. But it's just like a very off method. So the missing values are, so this is feedback that the user did not give. And we cannot say that it's even worse than negative. The lowest rating actually is 0.5, and we put 0, so it's even worse. The other problem is it's a dense matrix, and applying SVD to it is not scalable. So here, it's actually a very small data set. If you run a website, you hope, I wish you have more than 600, it depends, but if you want to do recommendation, let's say you want more than 600 visitors or users, actually I would say logged in users, because visitors alone, it's hard to track them, right? So, and items, well, maybe 10,000 items is reasonable to start with, but let's say, like, if you want to fill and apply SVD to a bigger and bigger tree, it just doesn't scale, it doesn't work. So what we'll do is we'll touch on trying to get an approximate matrix factorization using gradient descent. I don't want to go through this again. Yeah. So just who is not familiar with gradient descent? Okay, there's a few people. Thank you. Like, you didn't cheat. Everyone else did. So anyway, for you two, and maybe for everyone to refresh, I'll just explain what the gradient descent is. So you have a function. Okay, we'll start with Wendy. You have a function with one parameter. This function can have any shape. Usually what we're interested in is, for instance, a measure of a loss of an algorithm. So the loss would be, for instance, the difference between what you predict and the real value. It doesn't have to be convex. Convex means that if you take one point anywhere on the curve and another point, then it shouldn't cross the function itself, like the curve itself. Here, well, it's not the case. Like, ideally, yes, all the hypotheses, all the assumptions state that you should have a convergence function and so on. It's not the case. So yeah, that's why I took like a random function. But what we want to do is to find a minimum or the minimum, like a local minimum or the general minimum of this function. So what we start, the gradient descent approach is you randomly initialize the parameter theta. So you just take one point on the parameter space. So you got the evaluation of f on that point, And then you do it, you have a data set. So here we have, for instance, the rating, the ratings. And then here, I will do it row by row. So we call it stochastic. We'll just, we will update the value of the optimal theta for each row. And maybe I can look at the data set only one time, but maybe I want to do it many times. So here, for a given amount of time, I will compute the derivative of f on theta. So it is basically the slope of the curve on theta. Here it's a negative slope, okay? And then you update theta with the following rule. You move theta from minus alpha. Alpha is what we call an erring rate. It's just a step, like it's like a step in the algorithms, multiplied by the gradient. So multiplied by the direction of theta. Of the derivative of f on theta. So here this is negative, it's a negative slope, minus alpha, so you know that you have to increase theta. That's why, like, okay, you go from this point to this point. Okay, so, and then what you do, you repeat. So you get the slope again, so you get the red, and you update your theta. Yeah. What happens when you don't have one parameter, but many parameters? So here you have a function of many parameters theta, theta k. So here I just take 2 dimensions, theta 1 and theta 2. Well, you actually basically do the same. You randomly initialize all the theta, so you take 1 point in this hyperspace. You compute, so this time, so for a given amount of time, for all parameters, you try to compute the partial derivative of f on theta k, and you update the theta k with this rule. So theta k minus alpha of the partial by the partial derivative on theta k. And so, yeah, this way you actually, why we call it gradient descent. I mean, gradient because we compute a gradient, and descent because that's really like going down a valley or going down a ball or something. You really try to go down to find the direction where you'll fall. So your best friend here is gravity. So you imagine you here, and yes, you just let you fall. And then that's one way of finding the local minimum. So now we want to apply this to finding factorization of the initial matrix, of the initial spare matrix. So this time we do not fill the missing values. That's important. Like we said, okay, it's flawed, it's biased. We don't want to deduce feedback this way. So we do it a bit differently. So we won't go for orthogonal matrices. There are a few assumptions that won't hold anymore, but we still want just a matrix multiplication of user matrix by item matrix. So you initialize this item and user matrices, so the values in them, with random values. So that's your parameter theta. You compute the predicted rating, which is the product of the user and the item matrix. You compute the error, but the error is the difference between the predicted rating. So you take user I and user U and item I. You multiply the two hidden vector or latent vector representation of those user and item, and you compute the difference. And that's basically the you compute the difference with the actual rating you know. So this you do it only on the ratings you know of. You use the same update rule and you iterate until you've tired of looking at the data, or until you reach some kind of threshold, like the error goes beyond some threshold. So here, so the update rule, so the parameter theta corresponds to the weights of the user and item matrices. The function we want to minimize here is the sum of squared error. It's quite, we could call it loss. It's quite common in supervised learning. And this is exactly what I said. So R UI are the ratings that we know. R is the set of ratings that have been provided by the users. And you compute the predicted rating for this user and this item, compute the difference. That's the error. You square, and that's like you sum over all the ratings you know, and that's how you get the loss. The function you want to find an optimal point. So what you're interested in is the partial derivative on the parameters, so the user weight and the item weights. You do some magic, and that's what you get for each of the partial derivative. So if I inject it back in the algorithm, again, you initialize the value, all the values of the user and item matrix. You do n passes on the data. We call it an epoch. Usually, when we look once into all the rows, that's one epoch, and you do it maybe 1, 2, 3 times or more. For all non-ratings, then you update PU and you obtain you update the parameters, so the weight of the matrices, using this rule. And with this, I'll let you go back to the notebook. So yeah, it's just like repeating. Oh, I'm very sorry. I think I didn't give you the. No, it's here. It's okay. Wait. It could act as a flow. Yeah.
In the previous description, it was saying that this algorithm is stochastic gradient descent.
Yes.
And the one you just shown us is like gradient descent.
I call because I didn't want to. We don't need the word
Because,
stochastic, but
stochastic is like to avoid the local minimums, right?
Stochastic. Not necessarily. Stochastic is just like you update at each row, at each data point, versus batch gradient descent or mini batch gradient descent, where you'll update every I don't know 10 data points or every set of points. So so that's one extreme. So you update each for each row, and usually it's very chaotic. So for instance, you could go one direction and go back to one direction and then go back to another direction. Versus if, like the other extreme would be, you update, you just do one step, but for each step you look at all the data, and this is much smoother, but also much longer to process.
But
so that would be most of this.
But on the situation that random function that you were showing us, like how do you avoid like to fall into a trap of a local minimum?
Here I don't. That's a good question. I'm not trying to avoid that right now. For me, it would be like a more advanced step. But indeed, we're not free from that pitfall. So notebook. So this function, you might not need to know exactly what it does, but it will help the algorithm a bit later. Because if you looked at the data, maybe if you plotted all the IDs of the movies, for instance, of the items, you see that it's not continuous. You miss a few. So just to help it, I do a mapping between the IDs and the range of 1 to the number of item IDs, for instance. So you don't have to like look deeply in this one. On the other hand, what you should look at it is I just put the summary of the procedure, and I ask you to fill in the blanks here. So find the number of users and number of items of unique users and items in the data. Try to understand. So we randomly initialize the user and item matrices. We will look at a certain amount of epoch. By default, I put 3 because it's already quite long to run. You look at all rows in the data set. You get the user ID, item ID for this row, the rating for this row, and then your job is to calculate the error. And once you got the error, then you can do the gradient update, the parameter update. So yeah. Who has done it already? not yet. Okay, so I'll let you. What should help you is really this. That's what you're really trying to implement. So yeah, I was told that yes, indeed, if I just write those two lines in code, then so I update PU, and then I update QI, but QI also asks for PU, and in that case, I would update it on the already updated value of PU. So one way is to store the old value of PU first, and then use the PU old here. How you follow? I would think that on the long run it should give approximately the same result, but if you want to do it properly, then you should store the old PU value. So I'm writing it here, just like P old, and just make sure that here you use P old instead of PU. And I had a question also. Why do we use PU and QI like intervertly? So that's really because of the partial derivative, which is here. So when you compute the derivative of the loss function over PU, then you got the error term, and the error term actually contains a product of those two parameters, and you end up with both PU and QI in both partial derivative. So who has finished this part? 3, 4, 5, okay, 6, nice. Then you can also like get the estimate function just below if you want. And you gave a fix as well, Caroline. So what's the random score you got? Okay, plus 2. Okay. So let me maybe give you the one way of doing it. So what we were missing is the number of users, because the number of users and item will help us build the latent matrices. So one way to do that is just to look. So data is a data frame. You can get all the user ID from the data frame and just ask the number of unique elements. The same way for number of items. So during the gradient descent, you need the error function. So it's really the difference between the known rating, the real rating, minus the prediction of it. And the prediction is the product between, for a given user and a given item, the product of the two hidden vectors. And the update rule here, I just copy the formula here, which is PU plus alpha learning rate dot error dot QI. And here, so it's also QI plus alpha by the error by, so I would have put PU, but actually PU is already updated, so I put p old, but it's basically pu just. All right. Yeah. Okay. Yeah. No, you're right. Thanks.
Don't you also need a length there? Otherwise, you just get all the unique values. Just one
So.
data.
So you can use unique, just dot unique and then length, or just directly n unique. Yeah. And so let's say this function will actually give you out of the sparse metric the user and the p and q matrix, so the user and item matrices, and to then from this matrix get an estimate of the rating that user u would give to the movie I or the item I, given those two matrices. Then you just do the scalar product of the vectors for u and I, which is and p dot p of u q I transpose. Would anyone need me to put it on Slack? Okay, yeah, at least one person, so I just put those. Just check that it works. Yes, it works. So, yeah. Just do it here because it's easier. Or, yeah. The error looks like no, this, and the update is this. Buffer, and the estimate would be this. Okay, it's a bit brutal to just copy the few lines, but I hope you got it. All right, so let's compute it. Maybe I should have asked to do it before, but it takes a few minutes to do. So actually I can cheat and take another notebook that is already...
Question?
Yes?
So basically you're implementing this gradient descent because if your data set gets big, it will not complete otherwise. It will not fit in memory. But I was wondering, like, are you familiar with the truncated SVD?
Yes, it's another approach indeed. I'm not familiar with it, no. I just know it's another way to do, yes.
I'm not sure if I'm comparing apples and pears then, because I used like the SVD normal before, and
Okay.
it was indeed really slow.
Yes.
But then I used a truncated one,
Yeah.
which was like also recommended if you were working, for example, with like TF-IDF, which also generates really nice
Yeah.
big sparse matrices, and it was really fast. So I'm not sure if it would scale. eventually.
Sure. Would you know how to change the algorithms to do so? Would it be like in a few lines of code?
I think it's not. I think you use the SciPy.
NumPy, but yeah.
So it's
Oh, the SVD, yes.
in Slurm, so it's a bit.
Okay.
I have it on my screen.
So the question was about using a truncated SVD instead of SVD, and it's indeed faster. Okay, I just use, let's say, the first that I come across. Yeah. So, so it takes a bit of time to run, even for 3 epochs. But then, yeah, epoch 1, epoch 2. Then what we want to get is an estimate for all user item pairs. So for that, the only thing that you need to do is to do the dot product of these two matrices. And when you look at it, then you got a nicely filled matrix. You can the only thing is now you just because I had done a mapping of the IDs, you need to get the mapping back. So that's what this line is doing. And well, you just kind of apply it, and then okay, eventually you get the user item matrix with the proper user IDs and item IDs. Now I'm just going to run quickly the end of the notebook because I didn't want to torture you for the rest of it. So, and I didn't put too much comments as well. So if you want now to see the original rating for the user one, so it's what we did before. So here is not nice. It should be NAs, missing values. So, but yeah, basically you had 4 ratings, and now if you look at the new user item matrix that you filled, you get all the IDs filled. So you can look for, and then the new matrix gives you 4.2. You had 4 also here. Now it gives you 3.6. Yeah, okay. You had 6 here. You had 4 here, and gives you 4.7. So yeah, it's not an ideal. So maybe we need some. There are many things we will need actually. This is like the minimal version I could come up with of an approximate SVD approach procedure. But you would want possibly to add regularization. You want to have tools to easily split into train and validation set and maybe optimize some of the hyperparameters. So hyperparameters could be the number of epochs, the number of hidden features, the learning rate, for instance. So yeah, I didn't ask you to do it from scratch, but we'll see how to do it later. Now that you got this user item matrix field, you want to give recommendations. And for that, for instance, you just take all the predicted ratings for user 1. So for that, you just do .lock 1. You sort them, so you put the highest predicted movies on top. And for instance, you take the 10 highest predicted rated movies. You got movie IDs here, and then that's now where you can use the movie database information to look at what they look like. So these are the recommendations. So this user liked very old movies. I mean, seems to, that's what we predict. So we propose to this user very old movies around maybe drama, action, drama. Okay. Maybe it's nice to look at what was already rated by this user. So you just do the same, exactly the same, but with the first user item matrix with a lot of missing values. You sort them, and you get this. And it doesn't look it's superbly done, right? I don't see drama a single time. Yeah. So what could have we done better? A few ideas. Maybe we didn't train it enough. Maybe just 3 passes on data is not enough. Maybe actually I didn't look at the weights carefully, but maybe there are a few. There is some overfitting actually on the opposite side on the data. So for that we need regularization. That means try to limit the range of the parameters, so that there's not a few of them that is driving the prediction. We could optimize on the hyperparameters. Maybe there is a set of hyperparameters that works better. So yeah, to put this in production, you will need separate training and validation sets. And for that, I propose you to use actually now a library. So you have many on the market. I used Surprise because it is really dedicated to recommender system and Python. It is quite easy to read and understand the code. So yeah, so you need to install it. So on Collaboratory, it works smoothly. It might not be the case on your laptop. Sorry for that. So basically, Surprise allows you to define a data structure that gets a rating. So here, I define the reader, and I just need to tell it what's the range of the rating, and then I can import directly the data frame with rating into this format. I can apply SVD to it. I can do cross-validation. It's just a nice way of cutting your data set into a train and validation set, but instead of just doing one split, you do rotating splits. So you get in 5, and then you train with some of the 5, and you test on the rest, and you rotate. And then a very nice thing you can do with this, you can, like if you've used scikit-learn before, you can do the same procedure. So define, try to come up with better hyperparameters. So better number of epochs, better learning rate, for instance. And you can optimize on root, mean squared error, or mean absolute error. Here I will just pick the best parameters for root mean square error. And then you have, so once you got your best parameters, so that's what I do here, I get the best parameters from the grid search before. Then we can retrain on the whole data set with these hyperparameters that you defined. So that's what's being done here. And then you can use the predict function for a given user. So for instance, for user, okay, it takes some time, sorry for that. The funny thing is, so the predict function works for, you would expect that it works only for user and items that are seen in the database. Actually not. So I tried to use it on, for instance, a user that is not in the dataset. And it still gives me so a recommendation. So that's the predicted value. And why is that? Because actually the procedure in this library, it doesn't only give you predict values for a given item user, but it has also baselines. So there is a general baselines. Let's say the average, it's probably not exactly the average, but let's say baseline for all movies, all users. So actually, if you put a user, an unknown user and an unknown item, it will still give you a baseline value, yes. If you give it an unknown user and a known item, it will give you the baseline of all users plus the baseline for this movie. And oppositely, if you give a known user but an unknown item, it will give you the baseline for this particular user. So it is a nice way to even give a first try, a first estimate, even if you don't have data, like for a new movie or for a new user coming on your website. So that's, so I take one user. So the user ID 1. I look at what this user rated before. So I take the 10 best ratings, and I see, okay, drama again. I copied this from the surprise documentation, and this gives us the top, let's say 10, for instance, prediction for this user. So I built a test set which is only the values we don't know, that were not present in the rating list before. And okay. Yeah, I was a bit lazy, so I just here to see the nice matrix, I just copy pasted the list of user IDs into the data frame movies. So I let you run and then like compare. You should see a nicer match, let's say, between the already rated movies and the predicted ones. And to wrap up what we've done, so we had a list of user of ratings. So user rate this movie with this score. That was the DF ratings data frame. We pivoted it to get another representation, so the user item matrix. What we wanted to get is, relevant prediction for all the missing values, and we did so by applying a gradient descent procedure. One of the usual problem with collaborative filtering is, what do you do with new users, or what do you do with new products? So I showed you a way here. You can still get baseline and predict, for instance, for a new user coming, what, let's say, the average or the baseline that all the users predicted. And this you can do it as a byproduct of this factorization. Another way is, well, you can ask, okay, I just logged in, created an account on MovieLens, and then the first thing it asks, please, it wouldn't allow me to go further, please rate those movies, or give the score you would give those group of movies. And that's a way of getting initial information. Yeah. another way would try to get implicit feedback from the user, so let him browse a bit, just see which movie he browses and so on. I'll go for that. So the aim was really to get you build from scratch one factorization procedure. Then we used one library to speed up and to ease the process. Now, if you are interested to actually use the state-of-the-art techniques, I know of, there might be others, but I know of these three approaches. So BPR, triplet loss, so Bayesian, I don't know what. TensorFlow ranking package is very well done, and to recreate from Apple is also a very advanced package. And I'm sorry about this. I can send you a notebook if you're interested in checking a content-based approach, but it was a bit ambitious to try to cover both. So yeah, some pros and cons. Matrix factorization gives you relevant predictions for a given specific user, but it's computationally expensive. It's hard to work with sparse matrices, and it's hard to start with new users or new products, but there are some ways to go through. And now, well, I hope you enjoyed and you're not too bored. Please reach out to me on Slack if you have more questions or if you want the other notebook. Please try to run a notebook with your own dataset at home, and please also try those awesome libraries. So I'll give you a link to this presentation, and you can directly click on the notebook on Collaboratory and run them. So yeah, it's very easy. And yeah, many thanks. I hope you were able to ask the question during the talk. Otherwise, I'll be just right outside. Thanks.